In the last section, we discussed how to find the extrema values of a function, the maximum or the minimum value of a function. In this section, we'll apply what we learned there to some quote-unquote real-world problems. This first example will probably not strike you as real world, but it is a problem nonetheless. So let's find the maximum value of x cubed times y if x and y belong to 0, 1, and x plus y equals 1. Now, the majority of the time when we're trying to solve these application problems, we'll have a function we're trying to optimize. So we're trying to make this function as big as possible. But if you notice, this is a function of two variables. And since this is a single variable calculus class, we don't have the ability to take derivatives of multivariable functions. That awaits you in Calculus 3. So what will 90% of the time will happen, we'll have constraints. So we've got two constraints here. One, that x and y belong to 0, 1. So x isn't any bigger than 0 or any smaller than 1. Or vice versa. X isn't any smaller than 0 or bigger than 1. Same for y. And then we have the constraint that x plus y equals 1. So this is our wondering part of reading the problem. We kind of it's kind of circled our variables. We've done our work. We know what's here. We know what we want to do. We want to maximize the value. Okay, so how do we go about setting up this problem? So first off, let's write down what we want to do. We want to maximize. We want to find the maximum value, and I'll give it a function name. So f, and it's got two variables. So fxy is equal to x cubed y. So that's what we want to maximize. And we've got some constraints. We've got that 0 is less than or equal to x, less than or equal to 1. We have that 0 is less than or equal to y, less than or equal to 1. And we have that x plus y is equal to 1. So we've gotten all our facts down on paper. And now we need to figure out how to solve this problem. Well, since we're maximizing, we know we're going to be looking for critical values as well as boundary points. We've got our boundary points here. We know that right, x can't be bigger than or it's bound between 0 and 1, and y is bound between 0 and 1. So we've got some boundary points here. But again, in the last section, we've got way too many variables. So we're going to need to use our constraint, in particular this one, to reduce our dimension down, which should be pretty straightforward, since if x plus y equals 1, we know that y is equal to 1 minus x. And we can use this fact here and plug it into our original function, right? If y is equal to 1 minus x, we could put it in right here, and now this becomes a function of just one variable. So we reduce the complexity of the problem. We really want to maximize, and I'll give it a new name, g of x, which is f of x with y replaced with 1 minus x, which is equal to x cubed times 1 minus x, or that's simply x cubed minus x to the fourth. And what are our boundaries? Our boundaries, again, x can't be any smaller than 0 or any bigger than 1. So we immediately, since we're trying to find a maximum, we know we need to find critical values. So we should start listing off our critical values. Our critical values, we already have the endpoints. So we're going to add 0 and 1 to our set of critical values. And then the other critical values will be when the derivative is 0. So when is 0 equal to g prime. So 0, this is our interior critical points. So when the derivative is 0, which is equal to 3x squared minus 4x cubed, or factoring out an x squared, this is x squared times 3 minus 4x. And if this equation is true, if this is equal to 0, this tells us that either x is 0 or x is 3/4. Now, x being 0, we've already added that into our set of critical values, so the only new one we have here is 3/4. All right, so we've got 3 critical values. Now we just simply need to evaluate our function. We're going to evaluate g. Now, something to notice here, I don't have to go back and figure out what y is because I've got y constrained to this and I plug that into my function. So if I maximize g, that will also maximize the original problem. So I just need to find the value, the point where g is maximized, and so I will make my table. So I look at my critical values and I evaluate g on my critical values. So my critical values are 0, 1, and 3/4. If I put 0 in my function, I get 0. If I put 1 in my function, I'll get 0. So I'm putting these numbers, remember, I'm putting these numbers into g, right? So clearly, if I put 0 in here, it's 0. If I put 1 in there, it's 0. And then if I put 3/4 in there, I won't bore you with the calculations. I did this offline, but it'll be 27 over 256, right? And so this is my min, right? 0 is the smallest value I get in this interval, and here's my max. And going back to the problem, I wanted to know the maximum value. So let me write out what the solution would be. And the final answer is the maximum value of x cubed y with the given constraints is 27 over 256. All right, let's review. What did we do? We read the problem, we organized our work, I made sure to be clear what it is I'm maximizing, and I probably should have used some labeling to say that this was the constraint. I actually use a different color to make it stand out, but I'll try to use the good habit of organizing my work, being detailed about what the constraints are and what's the function I want to maximize, because usually that is where the most common mistakes that students make are in keeping track of what's the max or what they want to maximize and what are the constraints.